Okay, so the goal of this video is trying to understand Lewis structures and covalent bonding. So we're going to be able to see how covalent bonding happens in a molecule, then hopefully understand the difference between a polar and nonpolar covalent bond, and then we're going to look at applying this within a molecule by drawing out Lewis dot structures. So just to remind us, a covalent bond is when we share a pair of electrons between two atoms that brings them together. Okay, so for example, if we have something where we have nitrogen bonded to hydrogen, that line there represents a shared pair of electrons between those two atoms. Just a couple core informational topics that we want to make sure we're aware of. Bond energy is the strength of the attraction between the two nuclei based upon the shared pair of electrons. So if we think about the stronger the attraction, that would give us a stronger or higher bond energy. So the more that they're attracted to each other, the stronger that bond is going to be, and the more energy that would be stored in that bond. The next thing we think about is polar versus nonpolar bonds. So if we have a polar bond, that's where we have an unequal sharing of electrons. So if we have the unequal share between these two electrons in the covalent bond, now the amount of polarity, how polar that bond is dependent on electronegativity, which we're going to define below. So for example, if we were to have nitrogen bonded to hydrogen again, we wouldn't see these electrons being shared equally between them. What we'd actually see is that if we were kind of draw out what the density of these actual electrons look like, the electrons are going to kind of be more hanging out around our nitrogen over here. And so we would see more electrons on the side being shared by nitrogen versus hydrogen, and that we're going to see that relates to the electronegativity of those atoms. The next thing that we want to focus on is that when we're dealing with these bonding, we're only dealing with our valence electrons. So we're only going to be dealing with our valence electrons in bonds or the lone pairs also that we see within this. So we're going to illustrate this within Lewis structures. We're only focusing on our valence electrons. Number 4 is that the molecular shape of our molecule is dependent on the number of bonds and also lone pairs around our central atom. We're going to focus on that when we talk about shapes. So we see that it's real important for us to track about where our electrons are within bonds and how we go ahead and think about them being shared between two or more atoms. So to do that, we're going to illustrate this with Lewis structures. So Lewis structures are going to represent the valence electrons for an atom. So for example, if I have the fluorine atom, we would see that its electron configuration 1s2, 2s2, 2p5. And so what that do is that would tell us we have 7 valence electrons. So for us to represent those 7 valence electrons, each one of those is a dot. And we usually put a pair of them together to represent that they're paired up. And then it has one unpaired electron there. So we're not showing all 9 electrons, we're only showing the valence electrons. And that's because the valence electrons are going to be the ones that are actually bonding. Our hydrogen atom is just 1s1. So we'd have our hydrogen atom with a single lone electron, there. Then as we go and we're going to draw these Lewis structures that I have here below, a single line represents one bond, which is going to be sharing 2 electrons. This double line here represents 2 bonds, which is going to be 2 pairs of electrons. So that would be a total of 4 electrons here. These 3 lines here would represent a triple bond or three covalent bonds, so sharing of 3 pairs of electrons. And here again with our chlorine, we have 1 pair of electrons being shared between them. And then we notice there's, on each of these chlorines, there's 3 what we call lone pairs. So these are unbonded electrons. Now when we think about bonding, it's real important for us to think about how the electrons are shared. And it's dealing with this idea of electronegativity. So now let's go ahead and think about if we have hydrogen and fluorine bonded to each other. So if I have hydrogen fluorine, and I want to represent that they are going to be bonded to each other. Well, we see here we have electron here and electron here. Those are going to be the two electrons that are shared between our hydrogen and fluorine. So now we can draw a line between them, and we still have those lone pairs sitting there on our fluorine. Now, when we think about this, we want to answer, well, do they get shared equally? Is hydrogen seeing the electrons just as much as fluorine is? Well, we go back up to here, and this is just dealing with this idea of electronegativity. Electronegativity is the measurement of the strength that atoms pull on shared electrons. So real important here, shared electrons in a covalent bond. So they have to be in a bond for us to think about electronegativity. We don't think about lone atoms and the electronegativity that they would have. We think about them within a bond, what the electronegativity is. Within a periodic table, the electronegativity increases as we go up in the periodic table and as we go to the right. This is the exact same trend as electron affinity. Right? We think the electron affinity increases as we go up and increases as we go to the right. We'd see the same idea for electronegativity. So if we were to compare hydrogen and fluorine, we would see that the electronegativity of hydrogen is less than the electronegativity of fluorine. And that's because fluorine's way over here, right, and hydrogen's up here. And so we would see that because of that, that's going to lead us to drawing out this bond here. And maybe let's, instead of drawing out lines, let's think about the electron density. So we have our hydrogen and fluorine. And the more that there's electron density of our electrons, the greater that size will be. Okay, so what we would see, didn't draw it too well, but this should be fairly symmetrical. We would see that the majority of the electrons that are being shared are by the fluorine. So what that means is that our fluorine over here is going to have too much electrons for the number of protons it has. Well, if you have too many electrons, what that's going to do is that's going to give this side over here for our fluorine we call a partial negative charge. And that's just a lowercase delta to represent partial. So not fully -1, just between 0 and -1. And over here we'd have a partial positive charge because we have too few of the protons, the electrons to balance out our protons. And so we would see here that it would give it a positive charge. Now what that does is it creates two different poles. That's why we call this a polar bond. Polar bond is where we have unequal sharing of electrons. And what that does is that leads to one side that is partially positive and one side that's partially negative for the molecule, and in this case we are also thinking about the bond. So we'd see here this unequal sharing, the difference in electronegativity causes us to have this polar bond. Okay, so now we have this kind of basis level understanding of what a polar bond is, what a bond is, how we're sharing electrons, how we're going to represent electrons, and this all leads us into being able to write out Lewis structures. And Lewis structures are going to be able to help us define what electrons are being shared, what electrons are not being shared. And so let's go ahead and look at how we would define those. Okay, so I give us a description. This is available in your handout of how we're going to think through drawing out our Lewis structures. Okay, so we have this definition here. This is available in the handout that I have available on our assignment. So please go and grab that. Look through this as we're going to work through drawing out some Lewis structures. So now let's go ahead and look at some Lewis structures here. We're going to do some examples. Our first one here is carbon dioxide. So first thing we need to do is figure out what is our central atom. Well, our central atom is the least electronegative atom and is always, well, not always, excuse me, but usually our first atom listed. Well, we have 1 carbon, 2 oxygen. We would see that oxygen is more electronegative than carbon, and so that would tell us carbon's our central atom. So we're going to draw our central atom surrounded by those 2 oxygens. Now I just automatically drew in bonds because we know that they're going to be bonded to each other with at least 1 pair of electrons. But to figure out where our electrons are going to go, we need to find out how many total electrons we have. We're going to have one carbon atom, and each carbon atom has a total of 4 valence electrons. And then we have, you can think about this per carbon atom, and here we have 2 oxygen atoms, and each oxygen atom has 4 valence electrons per oxygen atom. And so that would tell us that we're going to have a total of 16 valence electrons. So that means I need to fit these 16 valence electrons in my total molecule. What we do is we start by giving all of our outside atoms, in this case our 2 oxygen atoms, everything other than our central atom, an octet. Everything wants to get to 8 electrons. That makes it happy. That gives it where it has a valence shell similar to a noble gas. Now what we do is we go back and we see, well, carbon doesn't have an octet, right? Carbon right here only has 4 valence electrons around it. It's got 2 thinking about this bond and 2 thinking about that bond. Well, then if we go and we look at that, well, that creates a problem for us because we don't have any more electrons that we can put. We can't just add 4 more electrons to carbon because we don't have that many available to us in this molecule. So for us to think about this, what we're going to do is we're going to see, well, what we have here is a deficit of electrons. So what we're going to do is we're going to form multiple bonds. So whether that would be double or triple bonds. And what that's going to do is that's going to allow us to give every atom an octet. So we look here, we have carbon dioxide. Well, carbon needs 4 more electrons. So what we can do is we can think of taking maybe this pair of electrons and now sharing it, and this pair of electrons and now sharing it. And now what that gives us is our carbon double bonded to the oxygen on the right, and then we still have those 2 lone pairs there, also double bonded to the oxygen on the left. And so now what this has done is this has given every atom an octet. Okay, so now they're happy. This is a Lewis structure that would fulfill the octet for every single one of our atoms. And so now we see here we got 8 electrons for oxygen. We have our 2, 4, 6, 8. We have 8 electrons around carbon. 2, 4, 6, 8. And then we also have 8 electrons around oxygen. 2, 4, 6, 8. So you notice we count those pairs of electrons being shared as being given to the carbon dioxide and the oxygen and the carbon here.